In today's lesson, we are going to continue our understanding of right-angled trigonometry. The goals of today's lesson are to construct a table of exact trigonometric values for particular sides, so for particular angles. And the second thing we're going to do is have a look at applications of right-angled trigonometry, elevation, depression, and bearings, all of which you have done previously in your school career. So this is all about just getting another sense of it. Just going to turn the lights off. Okay, now I was just going to give you a table full of values, but then it is such a nice set of values to create. I think I'm just going to very quickly construct some of the values for you so you can sort of see where they come from. Again, constructing knowledge is usually more powerful than not. Don't want anyone to use their calculator, so pop it away. So the reason why I asked that student to put his calculator away is because you're not constructing, you're just researching, aren't you? Using a calculator, but finding a value from a calculator does not actually get it into your head. It just makes you rely on a calculator. Hence, for example, a lot of people have walked in when I said, oh, we are going to look at exact trig values. They said, oh gosh, I can't remember those. Of course you can't, because you had a table and then you just referred to the table. But if you're stuck in a position where you need to construct them, if you know the triangle creation, it's actually pretty straightforward. Jeremy, I'll move you if I have to. Yeah? So these tricks of just what does a triangle look like that will allow me to get these values will be really handy. I'll tell you where they're really handy in a very mercenary way. When you're in a paper 1 exam where you won't have access to a table of values, nor will you have access to a calculator. Yes, you are expected to know them. But it's okay, because I'm about to construct them so you can make them better if you remember them. But if in a mind wipe you don't and you can remember the triangles instead, you're off to a good start. I'm not going to say anything more about that. I'm going to construct them. You're going to just have a look. You can follow on with me if you like and just get pen and paper out and construct the triangles as I go along. But I'm not going to stop, because literally I wasn't even going to be doing this, but I thought it's useful to do. Okay, what I do want you to do is fill in the table after we've done some constructions. Yeah, as long as it's quick.
Yes, very quick. The paper one, you know how we get that special booklet?
Yes, you get the booklet, you don't get this table of values. So whenever I think you'll need to know it off by heart, I will tell you. Otherwise, the formula booklet will have it, but this is one of the things that I won't. So let's have a look at the first triangle. This is the easiest one to look at. And it's a 45-degree angle. Okay, so I'm just going to do rough drawings here. So the heading is exact trig values, I suppose. I'll start off like this and then I'll zoom out when I look at more. So I'm going to construct a triangle with a right angle triangle with a 45-degree angle here, which of course makes this one 45 degrees as well. What kind of triangle is it? Starts with I, ends in isosceles. Very good. It's an isosceles triangle. Now, in all these triangles, for a very, very good, important reason, and if you did maths extended, you'll know why it's an important reason. For each of these triangles, I am going to have a hypotenuse of 1. Beg your pardon? For a reason I'll explain later, I'm always going to use a hypotenuse of 1. If you can't remember maths extended, it will, or if you didn't do it, it will click later on. Okay, but that's what I'm starting with. What I want you to do now, and I'm going to give you just a measly minute and a half to work out what those other 2 side lengths are exactly. No calculator. Go. Anyone who touches a calculator might cause me to go against one of the Quaker values, so don't do it. Pythagoras theorem. For those of you who are now experiencing the depths of panic and despair because you don't even know how to start, hey, don't worry, that panic's only going to last for another 40 seconds. You need me to repeat the two missing sides. Yeah. So the question is, you know, when you're in an exam situation, if you can remember it's a triangle with a side length of 1, everything else can be constructed from your previous knowledge. Yeah. Right now, we'll go through it. We'll go through it because you might get stuck and stuff, but it's actually not that bad. Okay, that's it. So you might have not got there yet. But to work out the missing sides, here we go. I'm going to call them X and X. They're the same length because, as I said to you before, it's an isosceles triangle, right? So that means those two side lengths must be the same, thank goodness, because if they were different side lengths, we couldn't do anything more. But because it's an isosceles, they're the same length. So that means by Pythagoras' theorem, I'm going to have the first short side squared plus the second short side squared equals the hypotenuse squared. So we've got 2x squared is equal to 1 because 1 squared is 1. I do my ones like that on the board so you know they're not L's. Divide both sides by 2 to get x squared is equal to a half. And therefore x, by square rooting both sides, equals the square root of 1 on 2. Now we don't like leaving it like that, okay? If you did that though, you're pretty close to perfect there. So I'll leave it zoomed out now, but it's not good enough. So x is equal to, now, if I'm square rooting a fraction, it's exactly the same as square rooting the top and square rooting the bottom. And what's the square root of 1? 1. So x actually equals 1 on root 2. And to be honest, when I remembered all of my trig values, that's how I memorized it, 1 on root 2. But a slightly preferred method, I haven't done the trig value yet, but I square rooted 1 to get 1, and the square root of 2 is root 2. Yeah? Yep. Sorry, and so I'm just trying to go really quickly, that's all. So this is okay, and this is how I would have left it. But these days, it's a little bit more fashionable to do something called rationalizing the denominator. And rationalizing the denominator means making sure that bottom number is a whole number or a fraction, a whole number basically. So if I multiply the bottom number by 2 and then do the same thing to the top, I get the square root of 2 on 2, because anything square root multiplied by itself is just that number under the square root sign. Is that okay so far? I'm rushing because it's actually, the construction's important. I'm video recording it, so you can always go back really slowly later, but I don't want to like absorb the whole lesson just doing this. So going back to my original diagram then, I'm going to erase x. No, I won't erase, I'll just put underneath. I'm going to put root 2 on 2 there, and of course it's root 2 on 2 there. So what does that mean? Our basic definitions of sine, cos, and tan are SOHCAHTOA, right? Sine is that ratio of opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent from the viewpoint of the angle. And I'm just going to use the bottom one because it will be the same from the top anyway. So when I have a look at sine, for example, it's now just a matter of using our trig understanding. The sine of 45 degrees is opposite, that's root 2 on 2, over hypotenuse, 1. Anything over 1 is just itself, and so the sine of 45 degrees is root 2 on 2. Opposite over hypotenuse. Cosine, same deal. The cosine of 45 degrees is adjacent over hypotenuse. Adjacent, bump, over hypotenuse. And so the cosine of 45 degrees is also root 2 on 2, thanks to the nature of an isosceles, all over 1. Anything over 1 is just itself, so it's just root 2 over 2. Thirdly, the tangent of 45 degrees is equal to opposite over adjacent. Opposite adjacent. Therefore, the tan of 45 degrees is root 2 on 2 all over root 2 on 2. Anything which is over itself is 1. So we have root 2 on 2, root 2 on 2, and 1 as being our 3 exact values for sine, cos, and tan of 45 degrees. Now, if you have a look at your little chart there, you will see that you've got the middle box there for 45 degrees, the middle column. You can now fill in sine, cos, and tan for those middle columns. You'll notice that there's it's been divided into 2. In fact, I should have not had that middle line there, so just use it as a line to write on. But the line underneath 0, 30, 45, 60, and 90 is deliberately left there. Do you know why? See how it says 0, 30, 45, 60, 90? Yeah, well, radians, let's call them what they are. They're radians. So later, we'll fill in the radians. No, but there's only one value. There's only one ratio, though. In other words, the sine of just pi on 4, for those who can't remember it, the sine of 45 degrees, I might be saying something valuable. You never know. I know I speak a lot of rubbish, but sometimes there's a nugget. Pi on 4 is the radian angle for 45 degrees. So all I'm saying is that the sine of 45 is the same as the sine of pi on 4. Okay, that's why I really wish I hadn't left that line in the middle there, because I don't want you to be confused. It is the one value. So down that column, you should have root 2 on 2, root 2 on 2, and then 1. All good? Yes, but we'll get to that later. Okay, so the next one is a little bit trickier to construct, but don't worry, it's worth it. I'm going to construct an equilateral triangle. Now, an equilateral triangle has all the sides the same length, and guess what I'm going to make those side lengths? Notice how I've put a big space between the bottom line and the 1 there? Now, an equilateral triangle has what angle? Because it's the same angle, isn't it? So it's going to be 60. Watch what I do here. There's a reason for it. 60 and 60. All of them are 60-degree angles. Now, the reason why I've sort of constructed it a bit weirdly is because I'm going to break this this triangle into a right angle triangle so that we can deal with it. And I'm going to do that by doing what's called, oh, don't do that, Richard. Dropping down a perpendicular bisector. That means the line goes from the top to the bottom at a right angle. And because of the nature of the equilateral triangle, it means that this is split in 2, the angle is split in 2, and it means that the baseline is split in 2. Is that okay? Okay, this gives us our new triangle. $60 degrees, 30 degrees, half, and 1. You've got 1 minute and 50 seconds to work out the missing side using Pythagoras. Pythagoras says the square of the hypotenuse is equal to the sum of the squares of the other 2 sides. Square one, square the other, add them together, and that'll give you 1. If it helps, I'll label it for you. There's an X. All you need to do is find that missing side. I'm not asking you to do anything else. You're welcome to jump ahead if you feel like you can. Yep. Quarter. 30 seconds left. No, 50 seconds left. I think I might have given you an extra minute. My mistake, though. I'm just going to give you 5 more seconds because I think I actually just gave you an extra 30 by mistake. Okay, so if I look at this triangle here, I'm going to have 1 squared is equal to a half squared plus x squared. So if I now figure that out, 1 squared is 1. Half squared is a quarter because a half of a half is a quarter. Right, so half times a half is a quarter. Plus x squared. I'm now going to subtract a quarter from both sides, and I'm going to rearrange the sides too because I want the thing I'm looking for to be on the left. So x squared is equal to 3/4. This is so cool. When I square root both sides, what do I end up with? I end up with the square root of 3 on the square root of 4, which is equal to root 3 over 2. I bet that value looks familiar to you. Root 3 on 2. Okay, so root 3 on 2 is the missing side length. I don't need to rationalize the denominator because 2 is a rational number. Sorry, yep, down on slide 7 now. Okay, so now I can go back and just fill that in just so it's clear on the diagram. It's root 3 on 2, and I can do the same thing again. On slide 8 now, I've got the sine of 60 degrees is equal to opposite over hypotenuse. Opposite over hypotenuse. So I've got root 3 on 2 over 1. I'm going to go sideways so I can fit them all into this slide. So that's going to be root 3 on 2. Yay. Cos of 60 degrees is adjacent over hypotenuse. It is adjacent over hypotenuse. So we've got a half over 1, which is just a half. The tangent of 60 degrees, this is probably the trickiest one to look at, is opposite over adjacent. Opposite over adjacent. Bit of manipulation here. Don't freak out. It's root 3 on 2, opposite over adjacent, a half. Now, I'm dividing by a half, which is the same as multiplying by 2, right? So that gives me root 3 on 2 multiplied by, I'm flipping the fraction, 2 over 1. Boom, boom, the 2's cancel out, shake the room. We're left with root 3. So the tan of 60 is root 3. I'll pause there because I know fractions are a weak point in the class. If you're not too sure what I did, now's the time to say, what the?
Wait, I'm sorry.
Finish the sentence, Richard.
Okay then, what the heck? Sorry? So here, remembering that this big bar here is that of the fraction is actually a division. When I divide by a half, our rules say if I'm dividing by a fraction, it's the same as multiplying by the reciprocal. Yeah, by flipping the fraction. So you can see the 1 over 2 has turned into a 2 over 1, and the divided by has become a times. Good, good, good. And then I've just cancelled down the 2's there. Isn't that cool? So that's 60 degrees done. Fill in your table. Yeah, you can see, I hope you can see that why I thought, no, I better not do it because it takes time. And then I thought B, actually it's worth doing because then you can do it for yourself. We do, and Jeremy, if you to sort of get you thinking along the right line, that's why I made sure the hypotenuse was always 1.
Yes.
It would have been actually easier for me to start off with an equilateral triangle of length 2, because then this would have made this bottom line 1 instead of a half. But it's because I was thinking a couple of steps ahead. Yeah, which is very unusual for me. So you're welcome, everyone. So we're going to do the same thing again. In fact, you know what? See if you can have a crack at it yourself. Sine, cos, and tan of 30 degrees. So we're at the top of the triangle now, and you're needing to use opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent to figure out your different things there. Tan's probably a bit tricky unless you're happy with fractions. Have you done that?
What?
Oh, you did. Sorry, it was your 60s. So you're up.
Yeah.
Keep going.
Isn't one of them undefined?
No, don't guess. Work it out. You've half remembered a fact,
Yeah.
and it's because tan of 90 is undefined.
Yeah.
We're not talking about tan 90. Yeah. So get out of the I'm trying to remember stuff and get into the get into the I'm constructing my understanding. I know it might sound pedantic to you, but it's really important that you're present with the material that I've given you. Just like that. It's good. The half. Oh, the root 3 on 2. Oh, yeah. Tan's awful though. The other thing I like about the triangles is it confirms some really tidy relationships there. You know that in a right angle triangle, if one of the angles is 60, the other one has to be 30. These are called complementary angles, two angles that add up to 90. So you can see that the complementary angles, you'll find that on your table of exact values, they are kind of complementary of each other as well. That the sine of 60 is the same as the cos of 30, and the sine of 60 is the same as cos of 30. Yeah. Now I won't talk to it, but I'm just going to do it on the board so you can sort of see it. I'm doing tan 30 on the board now if you got a bit lost with that one.
Oh, it's just root 3, isn't it?
No.
Cos 30?
Oh, cos 30?
Yeah.
No.
Root 3 over...
2. Root 3 over 2. Cos is adjacent over hypotenuse. What's adjacent?
Oh.
Root 3 on 2. What's the hypotenuse?
So that's tan then, is it?
Yes, but that should be, yeah, that will be tan.
Oh.
Have a look on the board.
I did the right thing wrong. Okay.
So excellent calculations, poor spelling, because you spelled cos. So you spelled a 3-letter word exactly wrong by 3 letters. Yes, it's all on the board now if you want to look.
Yeah, so tan 30.
Good place. Oh, no, Benissimo. I'm helping you prep for your exam.
I'm gonna ace it.
Yep.
Well, after all that Italian you would have had to speak, you'd be feeling a lot more confident.
Oh yeah, I do. I even like practice in my head when I go to sleep. It's really sad.
Do you know what I found myself doing after doing Italian for a number of years?
What?
I used to, particularly when the words were shorter, like and, I'd write it in Italian.
Oh really?
English and Italian. So I'd say like cat and dog, I'd just go cat, dog.
Oh my gosh, yes.
Because I was automatically translating in my head what it was anyway. So it was just shorthand. Yeah. Mm.
Oh.
It's not even smart. It's just a thing.
That's actually like it's the same time.
Yeah. It's not because I'm smart. It's because I'm lazy. That's what it is. Laziness is the mother of all invention. Don't let anyone else tell you things different. Okay, on the board. Great. why they are what they are. Yeah, it's always useful to do that. Theory of knowledge. This is called a constructivist approach to learning, where we construct meaning from the fundamentals because it sticks. Yeah, it sticks. Okay, so you'll notice, please fill in the 30 degrees. So the blanks that you'll have are 0 and 90. And the reason why they're blank is because 0 and 90 are impossible to define from right-angled trigonometry, because the maximum or the minimum value is x as x approaches 0, i.e. it never gets to 0, but it could be really close to 0. So you could have a 0.1 degree incline. It would be pretty flat, but you could do it. Or a 1 degree incline, or a 75 degree incline. All of those are legit, but as soon as you get to 0, the triangle would not have 3 sides, right? Similarly, if one of the angles was 90 degrees, then it wouldn't work. Well, I guess you've got the right angle itself. But the problem with the right angle itself is that from a right angle perspective, it's nonsensical in that the opposite is the hypotenuse. The adjacent, well, which one takes precedence over the adjacent for these two? So 90 degrees in right angle trig is not well defined, and hence we're going to leave those columns blank. In the next chapter of our trigonometry, we're going to be extending our understanding of trig values so that we can go beyond and below 0 and 90. So that will include 0 and 90, negative angles, and angles above. Now, this is going to be critical, right? And this is just a taster before we get into it, because actually, as it stands right now, we cannot work out if I was given, say, so if I was given 2 sides like this and an x, and I knew that this was 118 degrees, actually, we cannot solve that. Not only because it's not right angled, but because we don't actually have a reasonable definition for what does the cosine of 118 degrees mean. Now, some of us might say, I know what 118 degrees is because when I put it into my calculator, I get a value. But you don't know what 118 degrees is. You just know that the calculator can make sense of it. Well done. That makes you a calculator monkey. It doesn't make you a knowledgeable person, right? So what we'll do in next week is we'll extend your understanding to up to 180 degrees so we can then apply that understanding to a whole bunch of more triangles. That's where we're headed, okay? Sticking with 90 degrees because that's fundamental. Remember that tower I showed you yesterday? Understand the fundamentals, build up our understanding of right angle trig, then build it up a little bit further. That's what we're doing. Okay, if your brain hurts, that's not a good thing. I just want to see whether I need to push on or whether I can give you a little bit of work just to stop me from talking at you. Okay, so I'm going to pause the recording. This is the problem that you were left with. It's that thing there, and it's not as bad as I thought it was going to be. No, it's not too bad. So let me just take you through it really quickly, remembering that this is being recorded, so you can always come back and go through it slowly. Honestly, though, I'm just finding my voice getting faster and faster, so do slow me down if my voice is too fast. So in this triangle, that inside triangle there is yet again another isosceles triangle. So the first thing we can do is say, well, I know that that one is 45 degrees, as is the top angle, but I don't care about that so much. If I hadn't seen that, it is worth saying that around here is something that I could probably figure out as well. If I've got a side and an angle, I can always work out the missing side. Okay, in this instance, I've got an x. There are 2 ways I could figure out what x is. Number 1 is Pythagoras' theorem. Number 2 is to use my trig exact ratios. Because of the nature of where we're at right now, I'm going to do the exact trig ratio. So it's 45 degrees, and the x is the hypotenuse. So as soon as I identify that I'm going to need the hypotenuse, my next thing is to say, therefore not tan, right? I'm trying to uncover the thinking behind it. Therefore not tan, because tan is opposite over adjacent. Then I say, well, as long as I've got the opposite, I can use sine. As long as I've got the cosine, I can use, as long as I've got the adjacent, I can use cosine. In this instance, I've got both. So it doesn't matter. So I'm going to stick with your old pal sine. Please don't call it sin. And it's sin, so just then, sine of 45 degrees is equal to opposite, that's 8, over hypotenuse, x. Now, the sine of 45 degrees, I already know what that is because I memorized it from before. It's it's root 2 on 2. So I put root 2 on 2 instead of sine of 45, and I've got 8 on x. The rest of it is simply asking the question, can you manipulate an equation like this? If the answer is no, please practice. Please ask me. Please go. I'm happy to sit down and do a tutorial with you. I'm happy to show you YouTube videos if you prefer that way. I'm happy to give you problems to solve, but this is a basic skill. When the denominator is on the bottom, I multiply both sides by that variable. Sorry, when the variable is on the bottom, I multiply both sides by the variable to get rid of it from the bottom. Oops, beg your pardon. That should say 2, not x underneath the square root sign. I need those woes mentioned because it usually means I've made a mistake. I'm now going to get rid of my other denominator because I work better that way. So that leaves me with x root 2 is equal to 16. And therefore, x is equal to 16 on root 2. But I want to rationalize my denominator. So I multiply both top and bottom by root 2. And I get 16 root 2 on 2. And this is one of the reasons why it's nice to rationalize the denominator. 2 goes into 16 8 times. I get 8 root 2. Now, interestingly, I never had to work out what the square root of 128 was once then. Not even once. And that's because you went to your most comfortable place, which was you went to Pythagoras, because it's something you've been doing literally since year 8. But the only way you can grow is to be able to take on new tools and utilize the best tool. Did you choose an appropriate tool? Absolutely. If you did Pythag, you absolutely did. And if you followed through, you would have got the same answer as me, 8 root 2. However, was it the best tool? No. The next one is this big old triangle here with a Z. I'm going to try and do it in one square just to keep it all together. So I've got a 30, I've got an 8. Now, if you tried to do this via Pythagoras' theorem, you would have failed spectacularly, wouldn't you? Because you don't have two side lengths. You've got a part of a side length, and I really hope no one said, oh, it looks like it's half, and then made the whole length 16. If you did, that's an epic fail because you're making assumptions where it's not appropriate to do so. But what I can say is I've got an angle 30. I don't have the adjacent, but I do have the opposite, which means I'm forced to use sine, like so. Sine 30 is equal to opposite 8 over hypotenuse, z. Same manipulate. Well, actually, let's just work out what the sine of 30 is. The sine of 30 is a half. So we've got a half equals 8 on z. And the rest of it is manipulation. I would do this in one step and say that z is equal to 16. Okay? But just to take you through the process. Sophie's very pleased with herself. And she's made sure everyone knows. Z is equal to 16. Okay? Again, if you can confidently and fluently go from half equals 8 over z and z equals 16, I've got no dramas. You don't have to over communicate at this level of mathematics. But it's good to know that if you do just take a bit of extra time, you will get there in the end. Okay, any questions? What's y? Oh, was there a y and I missed it? Beg your pardon. The half not half bit. So if you said y equals 8, you're in trouble. I missed it. That makes it a little bit harder. Okay, so there's a bunch of ways you can do this problem as well. You could use Pythagoras' theorem because you've got one known side, you've now got another known side, and you've got this side here that you don't know. So Pythagoras' theorem would be appropriate, fairly reasonable, except that, it's place to think ahead. 8 plus y all squared is going to give me it's going to give me something to complicated to work out potentially. So I might leave that one and I might use trig instead. And with trig, I can see that, well, I could use cosine because that brings in the adjacent side, and I now know the hypotenuse. But I think I'll use tan, only for a very subtle reason. What is it? Do you reckon you know? Why would I choose tan over cosine? Okay, fair call. Where possible, I use values that are given to me rather than values that are calculated. Because if I've stuffed up Z, then I'll stuff up Y. But if I'm using values that I've already given to me, I'm less likely to make mistakes. Okay, excuse me for the other slides being missing, but I hope that's okay. I've now got the tan of 30 degrees being equal to opposite, which was 8, over adjacent, which was 8 plus y. Is that okay? Does that kind of make sense? Look at your chart. You'll see that tan of 30 degrees is equal to the square root of 3. And remember, in an exam situation, you could quickly mock up a triangle and you'd get there. So I'm going to replace tan of 30 with the square root of 3, and the rest is manipulation. Multiply both sides by 8 plus y. I'll keep those brackets in there. Did I stuff up?
Isn't it square root of 3 over 3?
Oh, sorry. This is me not referring to my diagram before. Like so. And then I'll get rid of my denominator off the left-hand side. So I'm left with 8 plus y root 3 is equal to 24. Multiply both sides by 3. Then I need to get to that y, right? There's no other way I can do it except, well, I could divide both sides by root 3, but I feel like I'm going to get more hurt if I do that. So I'm going to multiply by root 3. I'm going to expand the brackets. I'm now going to subtract the term that doesn't have any y's in it. And I'm thinking, oh, 8 goes into 24. I wonder if I'll use that later. Thinking ahead a little bit. And then I'm going to divide both sides by root 3 to get 24 minus 8 root 3 all over root 3. We're not finished yet though, are we? Because we need to rationalize the denominator. So in Ansel world, he's happy to leave it as it is. But we're not as slack as Ansel, are we, people?
No.
Of course we're not. We like to have a job well done, not a job half done, which is why you should never accept a sausage off the barbecue from Ansel. Or a sausage then. A sausage instead of a sausage. Root 3 is 24 minus 8 root 3 all over 3. And we'll expand it to get 24 root 3 minus 24 all over 3. I feel like there'll be a faster way of me doing this, but I'm going to keep going because I'm nothing if not obstinate. I can see there's a denominator of 3, and I can see that I know that 3 goes into 24, right? So I'm going to take out a common factor of 3 up the top there to get 8 root 3 minus 8 all over 3. And then that will give me 8 root 3 minus 8. You could take out the common factor of 8 if you wanted to get 8 outside of root 3 minus 1. if that floats your boat.
How long would this lesson need to take us to the exam?
There's just a little bit too much in it to worry about. But I'm not right now, just right now, I don't want us to think about what will I have to do in the exam, and I'd like to think about what makes for a good mathematical answer, just for a little while. Okay? Now, looking back on it, I wonder if I divided by root 3 first, it would have been faster. I suspect it would have been. So I didn't do it deliberately. I didn't, do it to teach you a lesson about going the wrong pathway, but nevertheless, it's a decent one to just pick up on since it's there. If I divided both sides by root 3 and rationalised it, I would have got it there a lot faster. You can do it in your own spare time if you want to, but it just goes to show that even an experienced mathematician can sometimes just pick the wrong pathway. But with perseverance, you get there anyway. It's just the long way instead of the short way. But yeah, in your spare time, divide both sides by root 3 and you'll get there faster, I reckon. Alrighty, it is now 2:35. You've had some practice time. I'm going to allow you to continue practicing for this lesson, and next lesson we're going to pick up on elevation and angles of elevation, depression, and compass directions.